So far, we have discussed control systems as being either open or closed loop, analog or digital. Yet, we can classify control systems in other ways, which have to do with their applications. Some of the most common applications are discussed next. Process control refers to a control system that oversees some industrial process so that a uniform, correct output is maintained. It does this by monitoring and adjusting the control parameters, such as temperature or flow rate, to ensure that the output product remains as it should. The classic example of a process control is a closed-loop system maintaining a specific temperature in an electric oven, as illustrated. In this case, the actuator is the heating element, the controlled variable is the temperature, and the sensor is a thermocouple, a device that converts temperature into voltage. The controller regulates power to the heating element in such a way as to keep the temperature, as reported by the thermocouple, at the value specified by the set point. Another example of process control is a paint factory in which two colors, blue and yellow, are mixed to produce green. To keep the output color constant, the exact proportions of blue and yellow must be maintained. The setup illustrated accomplishes this with flow valves 1 and 2, which are manually adjusted until the desired hue of green is achieved. The problem is that as the level of paint in the vats changes, the flow will change and the mixture will not remain constant. To maintain an even flow from the vats, we could add two electrically operated flow valves and their controls as shown. Each valve would maintain a specific flow of paint into the mixer, regardless of the upstream pressure. Theoretically, if the blue and yellow flows were independently maintained, the green should stay constant. In practice, however, other factors such as temperature or humidity may affect the mixing chemistry and therefore the output color. A better approach might be the system shown. A single sensor monitors the output color. If the green darkens, the controller increases the flow of yellow. If the green gets too light, the flow of yellow is decreased. The system is desirable because it monitors the actual parameter that needs to be maintained. In real life, such a straightforward system may not be possible because sensors that can measure the output directly may not exist or the process may involve many variables. Process control can be classified as being a continuous process or a batch process. In a continuous process, there is a continuous flow of material or product. Examples include the paint mixing example we reviewed earlier, oil refineries, and cement plants. I am referring to factories that make cement as opposed to plant that mix cement and stone to make a required amount of concrete. A batch process has a beginning and an end, which is usually performed over and over. Examples of batch processes include mixing a batch of bread dough and loading boxes on a pallet and making a batch of concrete on a building site. In a large plant, such as a refinery, many processes are occurring simultaneously and must be coordinated because the output of one process is the input of another. In the early days of process control, separate independent controllers were used for each process. This system is cheap and easy to isolate for local maintenance if process allows. The problem with this approach was that to change the overall flow of the product, each controller had to be adjusted manually. There was also little or no communication of data between controllers. In the 1960s, a new system was developed in which all independent controllers were replaced by a single large computer. This system is called Direct Digital Control, DDC. The advantage of this approach is that all local processes can be implemented, monitored, and adjusted from the same place. Also, because the computer can see the whole system, it is in a position to make adjustments to enhance total system performance. The drawback is that the whole plant is dependent on that one computer. If the computer goes offline to fix a problem in one process, the whole plant shuts down. The advent of small microprocessor-based controllers has led to a new approach called distributed computer control, DCC. In this system, each process has its own separate controller located at the site. These local controllers are interconnected via a local area network. All controllers on the network can be monitored or reprogrammed from a single supervisory computer. Once programmed, each process is essentially operating independently. This makes for a more robust and safe system because all the local processes will continue to function even if the supervisory computer or network goes down. For example, a local controller whose job it is to keep some material at a critical temperature will continue to function even if the supervisory computer is temporarily disabled. Increasingly, the components of a control system are being interconnected with the business office network in a factory, which allows the status of any process in the factory to be examined by any computer on anyone's desk. You might be able to sit down at a PC anywhere in the building and determine whether a particular photosensor on an assembly line has a dirty lens or how much current a particular motor is drawing.